Hi, today I'm talking about LeetCode problem 1339, maximum product of a splitted binary tree. As you can see, we're going to go over a solution that has 99.9% speed, or at least it got that result once. Let me explain the problem. We're given a binary tree, and what we want to do is split the binary tree into two subtrees such that the product of the sum of the subtrees is maximized. So in their example, they have 1, 2, let me use black. 1, 2, 3, 4, 5, 6. And they're asking, how can you split this into two subtrees such that if you sum all the values of the subtrees, the product is maximal? So in this example, I think it's 2 plus 4 is 6, plus 5, that's 11, times 10 is the sum of the other subtree. 11 times 10 would get a product of 110, and that's the best you can do. Their other example shows this subtree, and the best you can do is splitting it, this tree, the best you can do is splitting it into the subtrees 1, 2, 3, and 4, 5, 6 to get a product of 90. And they give another example, where it's just 1 and 1. So when I was thinking about this problem, the first thing I did is I just tried to think, like, logically, how do you know, what is the best way to split this tree? How do you know what the two subtrees should be? Like, do I have to think, what is every possible subtree and try that out? Well, no, probably not, because there are many possible subtrees. And the product says its constraints that there can be up to 50,000 nodes. So you can't really compute all the different subtrees of a 50,000 node tree. So that's out. Instead, I just kind of tried to work through it. I lost my position here while I was messing around. But I just tried to work through it like logically. I asked myself, okay, so let's take their example tree, and the sum is 21. How would I know what two factors made the maximum product? So I have this sum of 21. I guess I made it slightly easier for myself. I said, okay, well, if it's 20, I could imagine that 10 times 10, like that feels kind of intuitively like the best product, or the most valuable product, and that has 100. If I move it, like if I take 1 away from one side and add 1 to the other side, then I see that it gets smaller. And if I continue that, I see it keeps getting smaller. So 13 times 7 is smaller still than 12 times 8. And so then I just tried that with another couple of factors. So like 30. Well, 15 times 15, is that the most? 14 times 16, is that the biggest thing? And it turns out it is. And I think if I were like a better or smarter LeetCode practitioner, I would figure out like a proof for this, or I would say, why is this true? But to me, it just seemed like, well, okay, it is true. Like, we want to minimize the difference between the two sums, between the sums of the two subtrees. And so long as we can minimize the difference, then we've found the optimal case. And I tested that out here. I just went through each node and I said, okay, what is the sum? Let me try this slightly more legibly. 4, 5, 6. I said, okay, what is the sum of each? Okay, I didn't really achieve my goal of being more legible, but I said, starting here, what's the sum of each subtree? So these are my two subtrees, 6, 11, and 10. Okay, so I said for node 1, it's 10 and 11. And then I did the same thing for node 2. Okay, it would be this. Oops. For node 2, it's just going to be the 4 is one subtree, and then everything else is another subtree. So that would be 4, and then the other side is 21 minus 4, or 17. And then if I was at node 3, what would it be? Well, node 3 could have this subtree with just the number 6 and everything else, and so on. And so when I did that manual computation, I found, I guess, one, that this works. Yeah, I guess that's the most important thing, that this works and kind of how I should go about it. So I just implemented that logic in code here. So the first thing in my solutions object, I'm just going to initialize a dictionary to the empty dictionary. This is the solutions dictionary that I'm going to use for memoization. The next function that I'm going to use is what I call tree sum. I just want to find the sum of the tree given a particular node. So what's the sum of the root, what's the sum of the subtree, and so on. So if my node is nothing, then the sum is obviously 0. Here, if I've already stored my node in my solutions table, then just return what it is. And the point of this is memoization. The point of it is so I don't have to recompute sums for the same subtree, which I might otherwise have to do. So this is saying, rather than kind of recursively traverse the subtree every time I try to calculate the sum for it, just calculate it once and store what the value is. Yeah, I guess another way to do it would be to just make the sum a kind of property of the tree node. And I may try to modify that because I think that might be even faster. So yeah, here what I'm saying is the result is the value of my current node plus the tree sum of the left and right hand paths. Then I'm going to store my result in the tree node, and then I'm just going to return it. Now I wrote this function allSums originally to the logic that I wanted to capture here was to basically produce this table where I said, okay, at tree node 1, what is my sum? At tree node 2, what is the sum of the subtree? At tree node 3, what is the sum of the subtree? And I felt that I didn't need to get the tuple, or the pair, because the second value is always just the difference between the first value and the total. So when I know that the total is 22, knowing what the sum of one subtree is tells me what the sum of the other subtree is. So I thought, okay, I need to compute this table, but I realized after doing it that I actually didn't need to do it. So I'm not going to talk about this function. It's just how I was computing this table. So after I solved the problem and I was looking for ways to make it faster, I hit on the idea that I don't even need this function at all. I'll talk more about that in a second. So this final function here, max product, is going to be the one that answers the LeetCode question. So the first thing I do is just compute the total. Like I said, I need to know the total value of my subtree, and that's using my tree sum. And remember, because of memoization, it's not only going to calculate the sum for the whole thing, it's going to calculate the sum for every subtree as well, as we recursively compute the sum of the tree. We will store in our solutions dictionary the sum of every subtree. And so my max P, or max product, is just the max product that I've found so far. Then what I'm going to do is I'm just going to go through each value in my solutions dictionary. So the solutions dictionary is basically this structure, and that's what I was saying. I didn't need to have a separate function to compute this structure, because my solutions dictionary is a dictionary of a node to its sum, or like the sum of the values at that node. So I can just go through each of the nodes, or rather each of the sums that are in my dictionary, and use those to calculate the max product. So what I'm going to do is say, I'll say my current value is equal to the product of the value multiplied by total less value. So this is kind of the converse of value. We know that the sum of our subtree is 22. So when we go through each of the values, maybe the first value is 11. So the thing we're going to be multiplying it with is 22 minus 11. If the next value is 9, the thing we're going to be multiplying it to is 22 less 9. Oops, I guess that's 13, and so on. And we're just going to say if cur, which is the product of these two things, is greater than the max product, then we're just going to replace what max product is. And finally, we're going to return max product modulo this number. And the reason they wanted me to do that, the problem just says, in case the integer is too large, return the product modulo this number, this random number. So that is the source of this thing. Yep, and so like pretty much that runs as is. Let me go through the test cases that I used for this, if my test cases will load. So I used their 4 examples, and then I thought, what are kind of the special cases for a tree? So I thought about a tree that is essentially like a linked list. So like, what if it only has right-hand children and no left-hand children? 5, 5, 5. Would that work? And so that's what this is, where every left-hand child is null. And then the final thing, or the final additional test case, this is just another test case that I kind of put in. Well, what if I randomly add some numbers here? And then the final thing I put in is just this giant list, which is 50,000 nodes. And I just produced that, from my own Python terminal to just come up with a list of 50,000 random numbers. One thing it did for me is verify that I can solve the max case without timing out. Another thing, it's just kind of evidence that, if I could solve this giant problem, I probably have the logic correct. And the third thing it did for me, when I originally wrote it, I forgot to include this modulo thing. So that test case said, oh, right, I've got to include this. And these test cases let me get it right the first time I submitted it, rather than having errors, which I think is good. If I submit it now, I expect, well, 1, it'll work. I hope it'll continue to be pretty fast, although sometimes the times change on LeetCode. So like when I submitted it here versus here, it's the same code, but somehow I'm 30 milliseconds slower, and I've dropped down to 84 percentile for speed. The final thing I'll do here, let me just see if I can quickly change this from using, it just occurred to me, I was going to say I can change it from using the solutions dictionary to using a property on the node itself. But that actually won't work. I thought it would when I was talking. I guess I was saying, I was thinking, well, I could just say if node, whatever it is, Python has attribute, let's see, has adder, something like this, node, and we would look for the attribute like sum. Then we could return node sum. And otherwise down here, what we could do, rather than storing this in the solutions dictionary, we could say node sum becomes result. And so this would save me looking stuff up all the time in the dictionary, in the solutions dictionary. And maybe that would be marginally faster. But the problem with it is that I wouldn't construct this table that I was talking about with the solutions dictionary. Let me just see if this will run. So, can we do both? Like here, I'm not going to look stuff up in my solutions dictionary. I'm just going to return it from the node. I don't know if this will be faster or slower. I don't think it's a big enough difference. It doesn't seem to have made any difference really. But anyway, that's my solution to this LeetCode problem. 1339 maximum product of splitted binary tree. If you enjoyed this video, let me know by clicking the like button, say something in the comments. I'm going to try to, I try to solve a LeetCode problem a day. I don't always wind up recording it, but when I do, I post it on YouTube, and you can follow me if you want to see more of those. Thanks for your time. Bye-bye.